Section 1.5, we're going to take a look at another kind of model. So section 1.4 was all about linear models, the lines. Section 1.5 is exponential functions and models. So you've seen these before, maybe not recently. If you've had a college algebra class, you probably have seen them in there more recently than anywhere else. There are two different visual pictures that an exponential model could have. One is that it could look something like this. And this picture happens when the b value is bigger than 1. So every time that you are putting in a number and raising it to a power and that number b is bigger than 1, so it's 1.2, it's 77, it's 150,462,321. Whatever it is, it's going to look like this. Okay? What do I mean by look like this? Well, I mean it's going to taper off to the left and it's going to increase very quickly to the right. That's what I mean by look like this. The other possibility is that your b value is actually bigger than 0, but it's between 0 and 1. So it's a fraction, it's a decimal. And if it looks like that, it flips the graph. So it's increasing and going very high on the left, and it's tapering off at 0 on the right. It's always one of those two cases. B here has a name, and we're about to define it a little bit more on the next slide, but it is the percent change. Now, in general, if you're just given a couple of data points, which we will be in just a moment, you can find the percent change using this formula. F of B minus F of A over F of A times 100. Several weeks into COVID data reporting, all of a sudden the news media decided that percent change was really important and they started documenting it every day. It just showed up. I don't know why. New piece of information they reported. This is how they calculated it. I even double checked to make sure they were right, actually, for a few days there. You never know what happens on, public scales. All right, if you're dealing specifically with percent change and you have the b value already, you can take that b value and just subtract 1 and multiply by 100, and that gives you the percent change. So maybe I shouldn't have said over here it equals it, but more that it's related to it. It's keenly related. Probably a better description since I had the slide a little bit later. It's related to percent change. So if I have an equation that I'm already given a b value in, it works very nicely to find the percent change. And in fact, that's our first example. Our first example, 5 times 0.92 to the x. What is our b value in that equation? Yep, the 0.92. That right there is b. A is 5. Okay? A has meaning, but it's not what we're talking about right now. B. So if I were to calculate the percent change, which is what I'm doing on part B, let's actually do part B and we'll come back to part A so I can give you a justification for why I'm going to say what I'm going to say. We would take that 0.92, we would subtract 1, and we would multiply it by 100. What is 0.92 minus 1 times 100? Close? Negative 8, because you didn't multiply by 100 yet, Mark. It's negative 8%. Okay, so if I've already made the calculation and I go back to ask the question on part A, is it growing or decaying? And the percent change is negative. What do you think the answer is going to be from that perspective? Decaying. It's a negative percent change, right? Now, you can also do it from a graphical perspective over here. Which of these two cases is this example? The one on the left or the one on the right? It's the one on the right. Why? the b-value falls between 0 and 1. So there's two different ways you can think about how do I answer this question. You can think about it from a graphical point of view, or you can think about it from a numerical point of view. Either way you're doing it, it's decaying. Okay, so let's look at an example where we're given a little bit of data, and then we'll look at an example where we're given a table of data. This example talks about a subway token from 1997 to 2010. In New York City, subway token costs $1.50 in 1997. It has been estimated that the cost will rise by 7.46% per year through 2010. Find a model to predict for the price of a subway token from 1997 to 2010. So this piece right here, the 150, that's A. A is simply your initial value amount that you're working with. It was $1.50. So we have a function name. It's a subway, so I'm going to call mine S of x. Since we're working with subway tokens, you could do it T of x or M of x if you wanted money. I don't care. And it's 1.5 to start with, because that's A. I'm going to need some kind of a value raised to the x powered. Like that's what happens next. How do I decide what that value is? Close. 0.07. You're getting closer. So I'm going to take, it's all related to the 7.46. So you're looking at the right digits, okay? So this is the percent change, right? Yeah, I mean, and we have an equation over here. You might not have thought about it that way, but this is actually equal to the percent change. So if I knew the b value, I would subtract 1 and I'd multiply by 100, right? Well, this is 7.46%, and it equals b minus 1 times 100. That's what it is. So if you're thinking about going backwards, our goal is to figure out what in the world is b. What might you do first? Yeah, I divide by 100. So that's actually what you were already thinking to do when you mentioned that, Sarah, moving that decimal place, right? So there's that 0.076 that you mentioned before, b minus 1. Then what would you do? You'd add a 1. So you'd end up with 1.0746. Now let's talk about why that makes sense so that you don't necessarily have to do all of the details that I just did every time. This 1 right here represents that it was 100% to begin with. It's 100% the cost. It was the cost we had already. This, the 0.0746, is representing the increase that it had over every year. So this is the 100%, and this is the 7.46%, but it's put into decimal form. So over here on my equation, I have 1.0746. But models have 4 parts. A name and an equation, which we've done, right? Name and equation. What do I need after that? Yes, in the other order. Yep, we need the output first and then the input. So what is the output? What are we getting out of this function every time that we use it? The cost. So this is the cost of a subway token. And somewhere in there you need to use the fact that the cost is given in dollars. So in dollars, you could say this instead, maybe if you wanted to consolidate that a little bit, you could say dollars of cost, right, to merge it together a little bit better, whatever. But the dollars have to be in there because dollars is not the only way to measure money. Did you know that? In America, we can use cents, but there's actually other currencies as well, right? We got to say what we're using. Inputs next. What is the input? Awesome. So we need to say that our variable, which is our x, is being measured in years since 1997. Years since 1997. What's the last thing I need? No, I mean, I could put New York in there. It wouldn't be a bad thing to include, but if you didn't, it wouldn't. Huh?
Through 2010?
Through 2010. Okay, so I need to have an input interval. 1997 is marking my year 0. And this says that it's accurate, or it's be able to be used through the year 2010. So how many years after 1997 is that? 13. So we will go from 0 to 13 on our input. And on part B, it wants us to figure out what that 2010 price is. So how would I do that? Plug in the 13, right? S of 13, you can use your calculator to evaluate that. I recognize that we've talked about needing 3 decimal places, and we can write the 3 decimal places down. But on this particular equation, how many decimal places will I actually really be able to have my answer, my last and final answer, reported to? 2. Yeah? So right, this is 3.822. Why can I only use 2 decimal places? Somebody say it really loud. Yeah, our currency uses 2 decimal places. That's what our currency does. So this is in dollars. Dollars only has 2 decimal places. So a token at the Subway was $3.82 in 2010. Okay, any questions on that? All right. Last question for today. Consider the following table. The first question it says is, why is an exponential model appropriate? These are different years and the number of CDs that were sold in millions on those years. Do you guys even know what a CD is anymore? I'm not really sure my kids would. They would probably say, oh, it's like a DVD without the video. Something like that. All right, so old data, but that's okay. What you're going to do is you're going to put the data in your calculator. So let's go through this one, and then we will end on this note after this one today. So you're going to get back to your calculator. You're going to hit Stat, Edit, and you're going to clear out your lists. Okay, steps 1, 2, 3. Stat, Edit, clear out your lists. Enter the data into the list. Now here's the tricky thing. You really don't want to enter years in an L1, like ever. So there's 2 different things you could do. You could make 1993 year 0, and that would be fine. Or you can make 1993 year 3, because then it ends the way it already ends. My favorite is to make it 3. That's what I'm going to suggest you do for now. But if you choose to do 0, it's okay. So this would be 3, 4, 5, 6, and 7. So in my L1, I'm going to type 3, 4, 5, 6, and 7. And then the rest of the data can stay as is. 7.8, 9.3, 21.5, 43.2, and 66.7. Notice, when I did this, 3, 4, 5, and 6, and so forth, I made my input X years since 1990. Do you guys see that okay? If 3 means 1993, 3 is also 3 years past 1990. This is going to be the way I'm going to identify my input in my model in just a moment. If you choose to let it be 0, 1, 2, 3, and 4, or whatever, then yours will say X years since 1993. That was how it would be different. All right, these are CDs, so I'm going to call it C of X. And we're going to go back to the regular screen. So you hit second mode. Stat, calc. And if you arrow far enough down or arrow up and then to look at the bottom of the list, option 0 is exponential regression. So you're going to press 0 or you're going to arrow down. And again, you want to store it in the regression equation y1. Vars, y vars, function y1. And if you hit y equals, it'll put it all in there for you. This is 1.161 times 1.791 to the x. Sorry, it says y is an exponential model appropriate. I'm doing the next part, finding an exponential model. I'll come back to a in a second. Let me just move this. Okay. We'll fill in the details for that in a second. Let's go to why it's appropriate. Hit zoom fit, zoom 9, or sorry, zoom 9 is zoom stat. Make sure your plot's on. Mine just got turned off. Zoom 9. You're actually going to show the graph on top of the dots now. And it's not super perfect, but it's not bad. Without the graph on top of the dots, why would an exponential model be appropriate? And there's several reasons. First of all, it's definitely not a line, right? And so far, lines and exponentials are the only options you have. It's not one, it's the other. That's not a very good reason to write down. But these are some legitimate reasons why. It's concave up. It has concavity. And another reason is increasing rapidly as x increases or as x goes to infinity. Those are reasons why. Okay, give me one more minute. We'll finish up the last two details and I'll let you go, okay? What's missing? Well, we're missing the output, the input, the interval. The output is CDs sold. The input is X years since 1990. We already talked about that. And then my interval is not 0, is 3 to 7. That's the rest of the model, all those pieces. Part C says, according to the model, what is the percent growth, the percent change? Well, it's that B value occurring right there. So what do? Well, we take the 1.791, subtract 1, and multiply by 100. And if we do that, we will get that it is 79% per year. Does that make sense? Section 1.4, Section 1.5, over the weekend. The good news is you have 5 days and not 2 days. That really is good news. Katie will be there on Tuesday or Monday evening. You can also come see me in my office on Friday or on Monday as well if you need some help, okay?